Good afternoon, everybody. You might be taking your seats ready for the start of this afternoon's seminar. So welcome to the first Faraday seminar of this term. A special welcome if you're new to Faraday seminars. I think there are some new faces I see with us today. If you want to be kept in touch with everything that goes on in the Faraday Institute, please do sign up for our monthly newsletter. There'll be a sign-up sheet on the bookstore and as you go out. We promise not to pester you with all sorts of things, but just to keep you up to date on a monthly basis with all that's going on. A few other notices at the beginning. You'll see scattered around flyers for the rest of the seminars in this term. Please do take those away. If you can use them, you need more, please do ask them. We've got plenty more. Publicise those as well as you can. There are two more regular seminars. That's 2 weeks' time and then another 2 weeks after that. And then just to make sure that everybody's clear, the last one on that from Professor Alan Torrance is on a Wednesday, not a Tuesday, and it's not in here, it's in the Divinity faculty, and it's not at 1 o'clock, it's at 2:30. So just that is rather different. It's a new venture for us. It's one being done in collaboration with the Divinity faculty. Now, those of you who've been here a number of times will probably be used to the Faraday papers that are normally scattered on the top of the piano. We now have those in a nice stand outside. Those Faraday papers, and there's 19 of them, are written on some key subjects in science and religion. They are free, and we do have a lot of them. So do feel free. It does say please take one. If they're of use to you, then please do take them. It says free, it does mean free. I think that's all the announcements for the start. It's a privilege this afternoon to welcome our speaker, Dr. Douglas Kindschi. Douglas received his bachelor's degree in mathematics, and we've got to know the difference between math in the US and maths here. It's just divided by a common language, aren't we? From Hamilton College in New York, he did graduate study in the Divinity School in the University of Chicago, and received his MA and PhD degrees in mathematics from the University of Wisconsin-Madison, where he also completed a minor in philosophy. He's been at Grand Valley State University for 40 years now, and of those has served as dean for 28 years, and during his time as dean has established a number of different courses across a wide spectrum in science and philosophy. He's the founding director of the Kaufman Interfaith Institute, and in August 2015, Grand Valley named its new science building the P. Douglas Kindschi Hall of Science in recognition of his role in advancing sciences at the university. So we have somebody speaking to us this afternoon who has achieved considerable eminence. He's no stranger to Cambridge. He was visiting fellow in the Cambridge Interfaith Programme in 2013 and is back in Cambridge for the next 2 months as a visiting scholar in St Edmund's College. He only landed in this country yesterday, so I'm hoping our speaker can stay awake, and I'm sure that you will. So will you join me in welcoming Douglas?
Thank you very much. Can you hear me okay?
Yes.
Okay. Sometimes my voice fades, especially after jet lag. So if so, wave your hand and I'll crank it up a little bit. But it's a privilege to be back at the Faraday. I remember coming to these lunches and recognize some faces here. I used to attend the time I was here before on a regular basis. We're closer by now. We were living down on Grantchester Street before, so it was a hike, but now I'm at Westminster College, so it's just a 2-minute walk here. Anyway, I'm very pleased to be with you to talk about, is there a place at the science and religion table for mathematics? We see that most of the discussions going on in science mathematics are around physics and biology and more recently psychology, especially cognitive science of the mind and evolutionary cognitive science. But not too often do we hear about mathematics as something active in the science and religion discussions. There are some things happening. There was a journal recently that had a whole issue devoted to mathematics and religion, primarily from a Christian perspective. But I'd like to look at a little bit broader. Should I put my mic down or okay? Anyway, so what do people do at the science and religion table? They talk a lot about what is real. The scientists would claim that we have the corner on truth and what is real. Unless you can empirically prove it through scientific method, it's probably not real. Religion has, for millennia, claimed that it has an understanding of what is real, of the eternal reality. And mathematics probably has one of the strongest historical claims for what is real. Because Plato, back in the many centuries before Common Era, at his academy, it was said, had a sign, "Let no one ignorant of geometry enter here." Furthermore, he said in Plato's Republic, the knowledge at which geometry aims is knowledge of the eternal, not the perishing and the transient. We're going to unpack that a little bit as we proceed. Because following Plato, we have Euclid, who studied at the academy, went on to establish the School of Mathematics in Alexandria, and wrote the Elements, the famous geometry. 4 books of the Elements were sold in the history of publishing or the history of the world, other than perhaps the Bible. And Euclid developed his whole system on 5 postulates and 5 common notions. And we'll do a little bit of a geometry review here because it's important for the point I'm trying to make. The common notions, I think, are very common. Things equal to the same thing are equal to each other. Equals added to equals are equal. Equals subtracted from equals are equal. Things which coincide are equal. And the whole is greater than the parts. Nothing terribly profound. Then he had the 5 postulates or axioms for building his geometry. 2 points determine a line. Straight lines can be extended. A circle can be drawn given a center and a radius. All right angles are equal. So far, I think you're all with me, right? Pretty clear, pretty clear. Then the famous 5th postulate, which in Euclid's Elements reads as follows, that if a straight line here, falls on 2 straight lines, intersects these 2 straight lines, and makes interior angles on the same side, these 2 interior angles, that add up to less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on the side in which the angles are less than the 2 right angles. This 5th postulate, as you can see, is of such a different character, such a different nature than the other postulates and axioms, that it was a problem all through the history of mathematics. Can't we prove this? You know, we can prove so many other wonderful things. Shouldn't we be able to prove that? It doesn't feel like a common notion or an axiom that's intuitively obvious. Well, for hundreds of years, the attempt was made without success. We know, by the way, that 5th axiom, usually in the terms of Playfair, proved that it was equivalent, and that is given a line and a point not on the line, there is one and only one line which is parallel to the given line. That's the one that we're probably familiar with, and that was proven by Playfair to be equivalent to Euclid's 5th axiom. But even then, that's a kind of a problematic statement, because how do you know there's only one line? How do you know there's any lines? Maybe there's more than one line. How do we know when something produced indefinitely will never cross? But that was the axiom that was accepted and used by Euclid, or in later form by mathematicians. So, but from those 5 axioms and 5 common notions, Euclid proved 465 theorems, including that the sum of the angles of a triangle are 180 degrees. He said 2 right angles then. We talk about degrees. He proved the Pythagorean theorem that if you square the sides of a right triangle, it'll be equal to the square of the hypotenuse. He proved that there were an infinite number of prime numbers, numbers which couldn't be divided by anything other than 1 itself. And he proved in book 13 of the Elements the theorem about regular polyhedra. He proved that there could only be 5 regular polyhedra. Just to review a bit, a regular polyhedron is one in which each face is a regular polygon. In other words, all the sides are equal and all the angles are equal. And each vertex has the same number of faces. So if that's the regular polyhedron, Euclid proved that there could be only 5 of them. The tetrahedron, made of triangles and having 4 sides. The hexahedron we call the cube, made of squares. The octahedron, again made of triangles with 8 sides. The dodecahedron made up of pentagons with 12 sides. And the icosahedron with 20 sides, all made up of triangles. So, the science of Plato's day used those polyhedra, they were powerful concepts in the Greek idea, used those polyhedra to explain science, to explain what they thought at the time were the 4 basic elements of which all of the world was made: fire, earth, air, and water. Fire, they said, was made up of tiny little tetrahedra because they're pointy and they can break things up like fire does. The earth is very stable, so it must be made of the cubes of the hexahedra. Water was made up of octahedra, and water, because it's so smooth and flows, is the icosahedron. You'll notice there's one missing, and Plato said that was the dome over the universe, the 12-sided zodiac dome over the universe. All of this you can find in Plato's Timaeus. They even had back then a way of sort of what we would today call balancing equations. If we put it in kind of a modern notation, if I think of fire as F4, 4 because there are 4 triangles that make it up, and air is octahedron A8 because of the 8 triangles, and an icosahedron is W20, we can balance we can say that water is divided by fire and air, so we have water of 20 triangles could be broken up into fire and 2 elements of air. You can see that it balances you 16 triangles into 2 air plus 4 give you the 20 from the water. Or air could be divided into 2 fire. Or 5 parts of air condense into 2 parts of water. Again, it all balances. 5 times 8 is the same as 2 times 8. So there was a whole kind of chemistry of the day. Well, we look at this and think, how naive, you know. Our science has expanded so much beyond this. The mathematician Hermann Henkel says science tears things down and then rebuilds, whereas mathematics keeps the structure and just adds another floor, just adding more floors. So those theorems of Euclid still stand today, including this famous one about the 5 polyhedra. If you want a proof of it and give me a few more minutes, we could run through a quick proof, but I'll skip that. So the science and mathematics of Plato's day, science of Plato's day has been replaced many times over, but the mathematics still is valid. Euclid's proof still stands. Mathematics is the best and most certain description of reality, and this was the commonly felt idea for hundreds and hundreds of years. Including in the Renaissance, by the way, the polyhedra had such a powerful grip on the minds of scientists that Kepler's first attempt to explain the planets, and he was trying to understand the 6 planets. 6 planets, 5 polyhedra, there's got to be a relationship there somehow. So he embedded each of the polyhedra, nested them in spheres, and then looked at the differences between the radii of the spheres, and tried to use that as a model for where the various planets were in the solar system. It didn't work very well, and fortunately for science, he abandoned that project, but that was his first attempt. He went on with his revised theory to say it's not circles and spheres. This is another Greek idea, that the celestial bodies must be circles and spheres, must be describing them. He says, no, they're ellipses. They're square circles. It's not as perfect as the early Greek idea. And furthermore, he said that they don't travel at constant speed, which was a Greek idea. They actually vary in speed. As they get closer to the sun, they go faster. and as they get further away, they go slower. But the area that they traverse in any given time period would be the same. So this area in the, say, northern hemisphere winter, when we're closest, but it's going faster, that area would be the same as this area, but further away for a 1 month period, for example. I don't know how he even came up with the idea that area would have something to do with motion of bodies in 3 dimensions, but he proved that as well as Newton also proved it from basic principles. Okay, so Kepler said the laws of nature are but the mathematical thoughts of God. Galileo, contemporary, said the great book of nature can be read only by those who know the language in which it is written. And this language is mathematics. Newton, this most beautiful system of suns, planets, comets, could only proceed from the counsel and dominion of an intelligent and powerful being. This being governs all things, not as the soul of the world, but as Lord over all. Descartes, I'm especially delighted with mathematics on the account of the certitude and evidence of their reasoning. This impact even got on our famous skeptic Hume. Though there were never a circle or a triangle in nature, the truths demonstrated by Euclid would forever retain their certainty and evidence. You can see the power that mathematics had over the understanding of reality. So for centuries and centuries, mathematics could make the strongest claim that it had a handle on what is real. It's certain knowledge, the best description, the language of science. It's what God used to create the world. Then the big challenge comes. In the 1820s, the development of non-Euclidean geometry. Going back to that problematic postulate, the fifth one, about the parallel lines, people said, well, how do we know there's only one? Let's assume that there's more than one and see what happens. We'll find a contradiction, I'm sure, and that's a lot of mathematical proofs are proven by reductio ad absurdum. You assume the opposite, you find a contradiction, and then you prove the original premise. So they tried that. They also tried assuming that, but they couldn't get the contradiction they wanted. And finally, 3 mathematicians in Germany, Hungary, and Russia, Gauss, Bolyai, and Lobachevsky, actually worked out the logic of a geometry that had more than one parallel line, called hyperbolic geometry. And it was perfectly consistent. They proved theorems, just like Euclid did. One of the theorems was that all triangles have less than 180 degrees. They can't have 180 degrees. They always have to be less than 180 degrees. So they established a new geometry based on an alternate to that Euclid postulate. A few years later, Riemann said, okay, let's try it the other way. He assumed that there could be no parallel lines. And he proved and had a whole consistent geometry called spherical geometry. And he proved that triangles have to have more than 180 degrees. But these were consistent geometries. So that created what about this reality? Is the real world out there Euclidean? Is it hyperbolic? Is it spherical? What do we know? We can no longer claim that mathematics has brought us to the real truth, because now we have alternate mathematics. So what about that? The historian of mathematics, Morris Klein, said the importance of non-Euclidean geometry in the general history of thought cannot be exaggerated. Like Copernicus' heliocentric theory, Newton's law of gravitation, and Darwin's theory of evolution, the non-Euclidean geometry has radically affected science, philosophy, and religion. It is fair to say that no more cataclysmic event has ever taken place in the history of all thought. Pretty strong statement. But the more you think about it, he's got something there. Because it required an entire rethinking of mathematics. Mathematics was no longer than the sort of automatic, the one thing we can count on, the one thing we knew was absolutely true, the one thing that described the real world in ways that no other way could do. And that didn't require revisions all the time. The proofs were certain. It led to a big crisis in mathematics called the Foundations Crisis, of which there were three major responses. One was logicism from Bertrand Russell and Alfred North Whitehead, right across the street here, and intuitionism from Holland and Brouwer, and also formalism, which had the strongest impact on mathematics and philosophy for many, many decades, the formalism of David Hilbert. Hilbert's formalism, the way he got around this is he said, mathematics is just a game, played according to certain rules, meaningless marks on paper. So we go from certitude to meaningless. Quite a shift. He also said geometry of point, line, and plane could be substituted by tables, chairs, and glasses of beer. I'm guessing he was at a pub in Cambridge or a Rathskeller in Germany when he said that. But his point was that even the words are meaningless. We could use other words rather than points and lines, and we'd have the same game being played with the same kind of results. So, where are we now? Mathematics, the best, the most ultimate way to understand reality, or a bunch of meaningless, just a game, meaningless exercise. Are mathematical objects real? Are numbers real? Are points real? Are lines real? We've never seen a point. They have 0 dimension. It's impossible to see them. You've never seen a line. They have 1 dimension. You've never seen one. So, you've never seen a number. You make the distinction in mathematics between number and numeral. You've seen representations of a number, but you've never seen the number. You just see the symbol that represents that number. So are these things real? That became one of the big discussions in philosophy of mathematics. So, and if it's just a bunch of meaningless stuff, Eugene Wigner, Nobel laureate in physics, in a famous essay he wrote in 1960, the success of mathematics and natural sciences is something bordering on the mysterious, and there is no rational explanation for it. Now why? Because of that impact of formalism. It's just meaningless. It's just a game being played. So, but it's mysterious. He goes further and says, the miracle of the appropriateness of the language of mathematics for the formulation of the laws in physics is a wonderful gift we neither understand nor deserve. We've gone now from meaningless to miracles. It led to a rethinking of the whole question of realism in mathematics. And that's where I want to take us, because I think this is where we have something that can be very valuable at the science and religion table. How does mathematics function? What is the nature of mathematical talk? What is the nature of all of this? Is it real? Is it meaningless? What is it? Martin Gardner, in the foreword to Penrose's Emperors in Your Mind, said, Penrose has the courage to affirm a robust realism. Not only is the universe out there, but mathematical truth also has its own mysterious independence and timelessness. Gardner comment goes on about talking about the Penrose set in fractal geometry. Penrose finds it incomprehensible that anyone could suppose that this exotic structure is not as much out there as Mount Everest, is subject to exploration in the way a jungle is explored. But now we're back to the realism question. One way to try to unpack realism is to say, what was there before there were humans? What is real? Most people say rocks, mountains, trees. They were out there before humans evolved. Molecules, the moons of Jupiter were probably there even though we didn't know about them at the time. Electrons, but not things like chivalry and politics and grammar. These are things that we've invented, but the others have a certain reality. They were there before humans entered the scene. So, what about objectivity? We talk about science being objective. Is mathematics objective? Well, let's pretend that we're a scientist and we're going to study the nature of bats. And we know that they have incredible flying powers and they can do remarkable things when they fly. They must have just wonderful eyes. And then we look at them and no, they don't. We do some experiments, we put patches over their eyes and it doesn't seem to affect it. Then we say, well, they've got big ears, maybe that has something to do with it. We notice there's a squeaking sound, so we do experiments and we plug their ears and sure enough they can't fly like they did. So we do experiments with the object. We let the object tell us what is real. And that's the nature of scientific experimentation. Letting the object tell us, not bringing our own ideas, our own biases, but setting things up in a way that the object tells us what is real. So, is mathematics objective? Do mathematical objects exist? And if they do, where do they exist? And how do we experiment with them? A recent development in this whole thing is called structural realism. And it is the idea that we don't find objectivity in objects, we find it in structure. Philosopher Resnick says, in mathematics, we do not have objects with internal composition arranged in structures, we have only structures. The objects of mathematics are structureless points or positions in structure. As positions in structures, they have no identity or features outside the structure. So there is nothing to a point. There's nothing to three. There's nothing to a line outside of the structure in which we use those words to describe the structure, not the objects. I would argue structures existed before humans. It passes that realism test of what existed before humans. Structure is real. Relationships are real. Reality involves structure and matter. Before humans existed, there was a structural difference between a seedling and a full oak tree, even though they have the same DNA. There's a structural difference between oneness and two-ness. If you have one rabbit, you've got one rabbit. If you've got two rabbits, you've got a whole lot of rabbits. Oneness and two-ness have a real difference. And this goes right down to the basic DNA. The discovery of the double helix is a unpacking of that difference between oneness and two-ness. How oneness can be made up of two-ness and separated and replicate the DNA structure. Again, a discovery right here in Cambridge. In mathematics, we talk about one-to-one relationships. That's real. It's not just something we've made up. There's a reality if you've got a classroom with a certain number of chairs and a certain number of students. If there's more students than chairs, if there's not a one-to-one relationship, some of the students have to sit on the floor or bring in new chairs. Or if there's more chairs than students, you've got empty chairs. We don't have a one-to-one relationship here. We have some empty chairs. We have more chairs than people. And that, you can understand that, you can make sense of that without counting, without having a counting system. One-to-one relationship is even more basic than counting. The difference between a few M&Ms and a lot of M&Ms, a young child before he or she can count knows that difference. They know the difference between a small piece of cake and a big piece of cake before they studied volume and density and weight and all that. You don't have to have all of that to know intuitively that relationship difference is there. So, my claim so far is that reality is matter plus structure. Structure is based on relationships. Matter is real. Structure is real. And relationship is real. Just a little sideline here. We sometimes talk about the hierarchy of the sciences, the social sciences, and dealing with large groups of people, psychology, moving down to biology, cell biology, physics. As we proceed down, the objects of study get smaller and smaller, but the certainty seems to be greater and greater. The certainty in particle physics is very high level. So if you think of it in this term, you can then think of mathematics as having the smallest size, actually no size, and yet the certainty is the strongest. Just a possible observation. Mathematics is structure alone. Has the highest degree of certainty. But again, how and what sense is it objective? Well, the mathematician J.R. Lucas has said, mathematicians are not in fact concerned with a disparate set of entities, each with its own, but with patterns, whose structure is an essential part of their being, what they are, and whose interrelationships with one another could not have been different. We invent the terms, point, line, chair, your class, whatever, but the structures that they exhibit when put in the mathematical forms, that's inevitable, that's discovered. He goes on, realism that is more concerned with objectivity than with objects is a realism whose non-subjectivity is based on rationality rather than on opaque thinginess. I love the thinginess idea. The reason why mathematical truth is hard and ineluctable is not that it is a quasi-material object, which stands in the way of my getting past it and blocks my efforts and whatever I do, but that as I come more and more to understand what is at stake, I see that I should be acting unreasonably to deny its truth. Lucas argues mathematics is objective in that sense, not object-oriented, but it's unreasonable to deny. So we'll add one more. Mathematics is objective, using the concepts of Lucas. Mathematics provides a structure and a lens through which we view and make sense of the empirical data. The moons of Jupiter, most people would argue, existed before we discovered them. But Galileo's telescope was an invention, but the key was the structure of the lenses. It was the structure of the lenses that allowed us to see the moons of Jupiter. That structure opened us to new discoveries we wouldn't have had before. And that structure is also real. And mathematics acts as a lens. So mathematics is a lens that helps us make sense of the physical world. It's the lens through which we look to make sense of the world around us. It's the lens that science uses all the time in making sense of the world. We don't have to claim it's the mathematical thoughts of God. We can just understand the reality of that structure and the usefulness and the meaningfulness it gives us when we look at the world. Furthermore, I would say structure is non-reductive. We don't understand natural numbers by careful examination of one of them. We don't look at, if we understand all bats, we think if we look at one of them real carefully, we'll understand something about all bats. It doesn't work in structures. We don't understand a triangle by examining all the points. We need the whole structure. Language and meaning also work in the same way. I could see a bunch of symbols up there and they may not be meaningful to me at all. They're just marks. Or I can see the structure of those marks and recognize them as letters. I could even recognize repetition. I could recognize order. I could recognize those same points on the screen in a different structure, a different relationship, and identify them as words. I can identify them as concepts. I don't understand the word anymore by examining the letters or by examining the pixels on the screen. It's that structure that is bringing meaning to what I'm doing. I can see them as statements, in this case false, as physical laws, or as moral principles, or as philosophical claims. Each of these are non-reductive. We don't understand one level by reducing it to an earlier level. And I would argue that's true for structures and true for mathematical structures. So, meaning is not in the ink spots, but in the structure, pattern, and relationship of the ink spots, or in this case of the pixels. We don't understand Shakespeare better by analyzing chemical composition or the ink and paper. So, mathematics is non-reductive. Now, one more item to add to our discussion, and that is definition. Euclid attempted to define a point in the line. He thought everything should be defined. So he defined a point as that which has no part. A line is breadthless length. A straight line is a line which lies evenly with the points on itself. I don't know, does that help? Definitions have what we call the dictionary paradox. If you look up a word in the dictionary, and you say, well, I don't understand all those words, I'll look up all those other words. And you look them up and then say, well, I'll look up all of those. Eventually you'll end up with the word you started, or the only alternative goes on forever. Okay, So, you look in the Oxford Dictionary for the definition of a dog. It's a domesticated carnivorous mammal of the genus Canis. Okay, now I know what a dog is. You know, that's the dictionary problem, okay? In mathematics, we face that issue. Euclid couldn't really define a point. So in mathematics, we start with undefined terms. Terms are undefined. They are defined only relationally. They take on meaning only because in which way points and lines are related in the axioms and in the common notions. They take on reality in the relationships in the structures that we can prove in mathematics. That's where the undefined terms take on meaning, not by explicit definition, but by relational definition. So basic terms are defined relationally. Another characteristic I would suggest of structure is that it can have multiple physical instantiations. There could be various multiple forms, and I forgot to bring, but I have this really nice picture taken a few years ago by grandchildren. I can show it to you. And it's meaningful to me, maybe not to you, but it's meaningful to you, you can at least recognize it. And then if I'd remember to bring it, but thanks to time change, I forgot, I could rip that up. That picture doesn't exist anymore. No, that particular physical instantiation doesn't exist. It's still here. This time it's instantiated as pixels on a screen. And I can even get rid of that, and now it's gone? No, it's on the hard drive, it's on my flash drive. It's still there. That relationship, that pattern, that structure is there. It can be instantiated in multiple physical ways. So let's add one more. Structure can have multiple physical instantiations. Okay, let's bring mathematics now to the table. What are we going to learn from mathematics as we explore the science and religion discussion? Are we going to prove theorems about religion or theology? Can we claim rational certainty? Is religion just mathematics? Do we even understand religion by looking through the lens of mathematics? No, I'm not going to make any of those claims. What I am going to claim is that there are similarities and metaphors about how mathematics functions that can help us understand religion and theology. And I want to go through, some of you might be able to guess where we're headed. All of those things I've talked about mathematics could also be said about religion and theology. There are metaphors and models that we can gain from our understanding of mathematics that will help us understand certain theological and religious ideas. Neither are empirical. We don't see points. We don't go out and see God out there in the physical world. The definitions are relational. Yes, there are attempts to define God. They're not terribly successful. But what do our traditions tell us about who God is? It's usually in relational terms. God is shepherd. God is father. God is the hen over the chicks. God is king. Relational terms is how we come to understand our religious ideas. Is it objective? Not in the empirical scientific sense, but it's not object-oriented, but it is still, I could argue, objective in the sense that Lucas has described. It's non-reductive. You don't understand certain religious concepts by reducing them like the scientists do in a reductive approach. But I would argue it expresses something real, just as mathematics expresses something real. And it's open to multiple instantiations. There are various ways in which we can experience God in the empirical world, in a worship service, in Eucharist, in a song, in another religious culture. There are ways in which we can experience the reality through various instantiations in the empirical world. And maybe most important, it provides us a lens to make sense, not so much of the empirical world, but of the experience world, of our own experiences, of how we understand ourselves, our world, why we exist, the meaning, what is ultimate. It gives us the lens for that, just as mathematics provides us a lens for the scientist in understanding the empirical world. So let's bring mathematics to the table and see what we can learn from each other as a lens that focuses the structure of the experienced world. Phil Clayton in his book says, "My thesis is that religious beliefs are grounded at the onset in their ability to make the experience of the individual or group meaningful. The believer understands the world in a certain way. That is to say, he or she perceives a significance in a certain or all objects or situations that others do not. We see the world differently when we look through a telescope. We see the world differently when we look through a microscope. And the one doesn't necessarily work for the other. We see the world differently when we look through various religious and theological lenses. There's a little sidelight here. I want to just run off with some other ideas of how this might apply to other things. In mathematics, we deal with multiple systems. We have various geometries, various algebras, various number systems. We don't ask which one is true. Which one works? Which one makes things make sense? Einstein found that Euclidean geometry didn't work for what he was doing, but a spherical geometry did. We don't ask which is true, we ask which one helps us look through that structure to make sense of whatever it is we're trying to understand. I'm working now as the director of an interfaith program. I ask the question, could this be a model for looking at various religious traditions? Do we have to ask which one is true? Can't we ask, maybe they're a lens for certain cultures, certain people. They see things through that lens more effectively than it would through my lens. And that my religious understanding commitments are the lens that makes sense for me. Is it necessary that I ask which algebra is true? I can say which one is true for a certain situation, for a certain group of mathematicians, or which one is true for a scientist who's working on a certain problem. But do I have to ask which one is ultimately true? Do I have to ask those same questions when it comes to religion? I think there's a model here in mathematics that can be useful. Let's look at the humanities. In music, is it the note that I have to study, or is it the structure? Does the meaning in music come from the structure, from the relationship between the notes? Or in literature, what makes literature real? Why is a novel so gripping? Oh, it's because the characters are real. No. In most cases, those are fictional characters. It's not the characters that are real, it's the relationships and structures that the novel explicates. That's what makes that piece of literature so real to us, is that the relationships that are presented, not the objects, but the relationships are real. So I think this whole concept of relationship and how relationship and structure becomes the basis of how we understand mathematics is applicable to the science and religion table. Let's bring mathematics to the table. And as Lucas says, as I come more and more to understand what's at stake, I see that I should be acting unreasonably to deny its truth. Thank you.
Thank you, that was fascinating. Time for some questions, I think. And hands straight up, right at the back. I think Joseph's with the microphone, just behind you at the back there.
Oh, sorry.
Oh, we'll take one there and then we'll go back, since the mic's already there.
Okay, just have a couple quick questions. One, when you had the slide about increasing levels of certainty and decreasing size, where would you place like cosmology and astrophysics there? Because they're obviously very big.
Well, that's a good one. That's a good one. I'm not a cosmologist, but I would guess, I may be wrong, I would guess that a lot of what leads them to understanding cosmological principles, Big Bang, what happened at the first microseconds of the universe, that a lot of those things they were made possible because of studying the very small atomic physics. Now, like I said, I'm way outside of my range here. But I would guess that while obviously cosmology is making claims about the whole universe, it's really making claims about how it all got started. And the key to unlocking that, I would suggest, is at that particle level physics. But maybe someone who knows that better than I do could correct me on that.
Okay.
You want to either correct or challenge me?
Well, I would maybe the cosmology that focuses on the beginning of the universe, but I would say that astrophysics actually, a lot of modern, especially like non-relativistic astrophysics, focuses on things that are already kind of in motion, like big planets and big suns and big solar systems.
Yeah, it's applications of the theory that I would argue is dependent. It's a good point, it's a good point, I accept it.
That was a minor question.
No, I think it's
And my bigger question.
Just one, yeah?
Oh,
Go on, one big
Go
question
ahead.
then. Go on, your big question.
The other question is, so like in the late 20th century and early 19th century, late 19th century, early 20th century, there was sort of this crisis in mathematics where when they tried to put everything on logical foundations and axiomatize all of mathematics, there was a failure. And in fact, we found that like mathematics was not internally consistent on a logical basis. And then you had like, as a result, like Gödel's incompleteness theorem and things like this. So where would that fit into your framework?
Well, I think it fits very nicely into it because Gödel's, I mean, we're getting maybe beyond what most people will want to talk about it this way. But Gödel did put a big hole in the lotus system program. No question, his incompleteness theorem was pretty much put an end to that whole concept. But it wasn't that he proved that mathematics was inconsistent. He proved that you couldn't prove that mathematics was consistent unless you assumed it to be inconsistent. And it's a complicated logic sort of thing, but mathematics wasn't proven to be inconsistent. It was just proven that you couldn't prove it. And I think that was a very important discovery in what I would call the breakup, the results of the breakup of the certainty of mathematics from the non-Euclidean geometry of almost 100 years earlier, the 1820s.
Yeah.
So yeah, it's sort of Gödel kind of put the final nail on that topic. Good point.
Thanks for that beautiful elucidation.
A little louder, maybe hold it closer.
Thank you for that beautiful elucidation. While we acknowledge the intrinsic cognitive significance of various religions, it's not relevant to be able to evaluate them against each other. For example, when you have religious ideologies that propagate humanizing others who don't believe what you believe, should we not describe those as inhuman?
No, your point, if I understand it clearly, is that it's not that they're totally independent and there's no basis on which they can be judged. Is that what you're saying? I would agree. I would agree that we can't judge a particular religious system because it disagrees with my religious system, just as I can't say, well, this algebra must not be correct because it doesn't have a parallel postulate. You know, there are ways in which it can't be compared, but we can certainly compare mathematical systems and religious systems in terms of what the fruit of that is, what the product of it is. And there we're moving very clearly in the theological world into a basic theological and human understanding. Our religions make sense of the world, and some religions don't work for us, and we need to struggle to understand why the implications of what they say, is that coming just from their religion, or is it coming from other things? And yes, we do have a right to judge those things. I'm not a relativist. I'm a long ways from a relativist. I think we do have a right, and not only a right, we have a responsibility to judge, but we don't judge them on the basis of my particular lens, that is the ultimate. I hope that's helpful.
Just a little bit further forward and then we'll come to the front.
So regarding mathematical realism and non-realism, as far as I can understand you, you pointed out that the problem with mathematical non-realism is applicability of mathematics in the real world, physics and so on. How does realism explain that any better?
Well, let me see if I understand. The problem with mathematics being treated strictly as a game, a meaningless game, is the problem that Eugene Wigner pointed out. That why does it work so well? Why don't we use chess or soccer as the game to explain? Why don't scientists use those game rules? There is something very profound about why mathematics does that. Now, the Platonic realists like Penrose and others, would say it's because the mathematical objects are real and they live. The question is, if you claim that they're real, where are they? Where are they real? They're not in the empirical world. They live in a Platonic world. I had one person I interacted with who claimed that there are 5 worlds. There's not only the empirical world, but there's the mathematical world. There is the moral universe. I don't know what all 5 were, but I would prefer to say there is one reality, but there are multiple ways of understanding it. And the fact that mathematics is so powerful in helping us understand that means it has a kind of realism. Not that those mathematical objects are in another world, but it has a kind of realism in the sense that it's unreasonable to deny the value in the Lewis sense.
Hello, thank you very much, Professor, for a really lovely talk. You said that there was a fundamental difference between oneness and two-ness, that anybody would understand that difference. Now that got me thinking about a very, very ancient Christian notion, and indeed it's available in Indian faiths as well, that when God created the world, he created 2 worlds. He created the visible and the invisible. He created the spiritual and the physical. And the spiritual was the stuff that he was made from, and the physical was the, all the stuff, the clay. In man, and they existed, as Gregory Nazianzen said, each within their own borders. In man, and uniquely in man, he gave it the chance to merge. And he says that the man was a beautiful microcosm, harmonious, beautiful, everything working and lovely. And within this little world of man, he placed the greater world of the spiritual, the macrocosm. He placed himself. And the whole purpose of mankind on earth, this was the original Christian belief, the whole purpose of man on earth was to mediate between these 2 worlds, to see that there was no me and thou, there was I and thou, there was oneness, there was unity, it was to overcome, and that was the fundamental role of man, and that led to the whole thing about deification and all the rest of it. And I just wondered, would maths, with its insistence on its separatedness, would it be difficult to understand oneself as that, in that mediating role, that deification role, which is, as I said, a basic principle of Christianity, if you have this mathematical outlook of the numbers separate, even though they exist within structure and relationship and all the rest?
That is one way to go, and that's what I've hinted already is not the way I go. One can posit that there is a Platonic world that numbers and lines and points exist, and we just see shadows of them. It goes back to the Platonic. We live in the cave and we see the shadows, only we don't see the real. The real is out there. And one can posit that those mathematical objects are out there in a Platonic world, in another world. One can also posit, as you pointed out, as early Christians did, and other religious traditions, that there is another world other than the empirical world, and that is the spiritual world, and that there are ways in which those can come together. I don't find that helpful to my way of putting things together. Part of the problem is because of what's happened in the history of science and religion. We have found that concept, it keeps getting more and more challenged. Evolutionary biology has now helped us understand that there are altruistic aspects in the evolution. There are spiritual understandings that can be seen as evolutionary. So I think as we become more integrated in our understanding of how religion and science works together, I personally think that I can't keep them as radically separate and uniquely combined in humans. I don't find that working for me. My approach would be what I've already hinted at, is that there is one world, and that world is material and relational and spiritual and all these other terms we give it, and we can look at that one reality through various eyes, through various lenses. I can experience that one reality spiritually in worship, in other ways. I can experience music in certain ways that maybe a scientist, a physicist would not experience. But I would like to say that that's one world. It's all part of that one world out there. And I don't, you know, there certainly is a strong tradition for what you described. And if putting it together makes sense for you and that gives you meaning, then I don't want to argue against that working for you. That's a system, that's a structure that makes sense for you. My structure would be just a little bit different, and I've told you why.
Thank you. I see another hand.
Thank you. You referred to classes of objects and concepts which were post-human and pre-human, and you put mathematics into the pre-human category. You also said that mathematics is something that can be explored and discovered. But looking further back, would you say that mathematics was created by a creator God, or that it was something that just is?
Okay, let me clarify. I did not say that mathematics was pre-human. I would say the structures that mathematics exposes is pre-human. The structures, the patterns, the relationships are pre-human. Mathematics is a human activity of putting those patterns, understanding those patterns more deeply, of making sense, giving language to those patterns. The patterns existed before, the language didn't, the mathematics didn't. And so I would say that in the creation, God created a world not just of matter, but a world of matter and structure. That is the nature of the real world. It is a matter and structural world, and we can study it from the matter empirical side, or we can also study it, as mathematicians do, from the pattern side. And I'm suggesting that there are other ways of knowing that also are helpful to think of from the relational pattern perspective, like I've suggested, interfaith, music, literature. That can be, we've been overwhelmed by the success of the empirical sciences to the point that some of them would famously argue that that's the only reality, is what they discovered. I'm saying the reality is much, much bigger, and we have multiple ways of accessing that reality, different ways of learning about it. Hope that helps.
Thank you. I think at that point we'll draw our time to a conclusion. There may be one or two questions you can just field afterwards. We'll draw our time. Can you join me in thanking Doug for a really fascinating talk today?